Water at 20 degrees C flows through the elbow shown and exits to the atmosphere. The pipe diameter at 1 is 10 centimeters, while the diameter at 2 is 3 centimeters. At a weight flow rate of 150 newtons per second, the pressure at 1 is 2.3 atmospheres gauge. Neglecting the weight of the water in the elbow, estimate the force on the flange bolts in section 1. So the first thing that we're going to do is let's draw a control volume. And I am going to draw the control volume right here at point 2, orthogonally to the output. Here at point 1, I'm going to draw it orthogonally to the input. I do that so when we do our conservation of mass, conservation of linear momentum equations, we'll be able to make that one-dimensional inlets and outlets. I also do it because I know the diameter here of the output. I know the diameter here, I know the pressure there. So I want to be able to use that information, so I have to have that control volume go through there. Rest of it doesn't matter because nothing's going on, so we'll just close it off. There's our control volume, where we're going to be looking at everything coming in and coming out. So if we look at our information, we have water at 20 degrees C. We can sit there and look that up. What we're going to need is the density, or the specific weight, and the specific weight of that is 9790 newtons per cubic meter at 3 degrees C. Excuse me, at 20 degrees C. The density at 20 degrees C would be 998 kilograms per cubic meter. So we also have that the diameter at 1, I'm going to use the diameter symbol, is 10 centimeters. And so 10 centimeters would be 0.1 meter. The diameter at point 2 is 3 centimeters, so that's 0.3 meter. So I'm converting these all into meter now because I know that's what I'm going to need. So I have a weight flow rate. What is a weight flow rate? Weight flow rate is just the mass flow rate times gravity. So instead of a mass flow rate, we have a weight flow rate of 150 newtons per second. Now, the next thing, we're given the pressure. We're given the pressure in gauge pressure. We're going to leave it in gauge pressure because everything will end up canceling out. So that tells me that my pressure at 1 is 2.3 atmospheres. And so it is 2.3 atmospheres. An atmosphere is basically sea level atmospheric pressure. So 2.3 of those, we end up multiplying out our 101,300 by 2.3. And so once we do that calculation, we're going to end up with 233 kilopascals, kPa. Pressure at 2, we're dealing in gauge pressure, that's atmospheric. And so at gauge pressure, we are talking 0 kPa, because atmospheric pressure is 0. I'm going to put that little G there just to remind us that is gauge pressure. Okay, so now we have our information from the problem. We have our control volume. Let's make our assumptions. Do that right here. And so what are we assuming? Well, we have a couple of assumptions we can make. The first one is we're going to assume that we have a fixed CV. I know it's a fixed CV because I drew it. Second one is one-dimensional inlets and outlets. I know I have one-dimensional inlets and outlets because that's the way I drew it. Next one is steady flow. Why can I assume steady flow? There's nothing in the problem that says the flow depends on time. And the last one, I'm using water at 4 degrees C, so I'm just going to make the assumption that it's incompressible or density is constant. So that allows us to quickly use our equations. So one of the first things that we're going to do is we will do conservation of mass. Now, almost all of these problems that we do is really always going to start with conservation of mass equation. So conservation of mass equation we know is mass flow in is equal to mass flow out. Once we make those three assumptions. And since it is incompressible, we know that means Q in is equal to Q out. So we need to calculate out Q. What is Q? Q is the velocity times the area. So if we look at our weight flow rate, we divide that by gamma. What is gamma? Gamma is our specific weight. Rho times gravity. So our mass flow rate is m times g, which is our weight flow rate. That guy there is rho times gravity. Gravities will cancel out. We have the mass flow rate divided by the density. Mass flow rate's rho VA. Divide by the density. It's going to leave us with VA, which is going to leave us with Q. So we'll take the weight flow rate, divide it by the specific weight of the fluid, and calculate out Q. And so Q. As we look at it then, Q is going to be equal to the weight flow rate divided by our specific weight of the fluid. So 150 newtons per second divided by 9790 newtons per cubic meter. If we look at the units, that's going to work out to be cubic meters per second, which would be a volumetric flow rate. And when we calculate that out, 0.053 cubic meters per second. And so, because VA1 is equal to VA2, and that's all equal to Q, because Q is going to be constant, because Q coming in is Q coming out, we've only got one input, one output, so it's going to be a flow right through there. So Q is equal to V1A1, which is equal to V2A2. We don't know the velocities, but we do know the areas. Now that we know Q, we can calculate out what the velocities are. So V1 is going to be Q divided by A1, so 0.0153 cubic meters per second, divided by our diameter at point 1 was 10 centimeters, so we'll calculate out the area, 0.1 meter squared. And when we plug all those in, we look at the numbers, we're going to end up with meters per second, and so we have 1.95 meters per second. So we're going to need that, so we do the second one, so V2 is Q divided by A2, 0.0153 cubic meters per second divided by pi over 4 times 0.03 meters squared, and so we end up getting 21.7 meters per second. So if we look at conservation of mass, all the mass going in has to equal all the mass going out. I've restricted my exit in diameter by quite a bit, and so the only way this balances out to be able to move the same amount of mass out as I'm coming in with a smaller nozzle is I have to speed the flow up quite a bit. Okay, so that gives us our velocities. Now let's start looking at conservation of linear momentum. Now with this one, we are looking at just the x direction. The problem did not ask for y direction. So what do? We start taking a look at it, and then the sum of the forces in the x direction. Well, that's going to equal, if we go back and look at the picture, let's look at what forces are acting on the control surface. Well, I have the velocities coming in and out. We'll take care of that with the other part of the problem. I have pressure forces pushing in on the control surface. I also have the force of the bolts pushing out. So now we can take that and plug that into our equation. Now, since we have gauge pressure, we don't have to worry about that. So we're only going to have to worry about what's going on at point 1. So the sum of the forces in the x direction. Now, this is a vector equation, so we have to worry about direction. So our force of bolts was acting in the negative direction. Negative force of the bolts. Our pressure is acting in the positive direction. But pressure is a force density, not a force, so we're going to have to multiply that by the area to get the force. So that's the sum of all of our surface and body forces because we're ignoring gravity, and that is going to equal mass flow rate at point 1 times the x velocity at 1. So remember, u is x velocity, v is y velocity, w is z velocity. So saying u1, or u, is the same thing as vx, v is the same thing as vy, sorry, not z, w is the same thing as vz. It just saves some writing. So that's everything coming into the system, which needs to be negative, plus everything coming out of the system, m2, u2. Now remember, these are vector components, so we're only looking at the x component of the velocity. Now, m1 and m2 from the conservation of mass, we know that's the same thing, so we can pull that out and say, okay, well, m dot is going to be U2 minus U1. So now we can start putting things together. We're trying to find the force of the bolts. We have the pressure in the area. And now we have to put this stuff together. So the first thing that we do is we can look at m dot. M dot's going to be the same at 1 or 2. It doesn't matter which one we do. So let's just do it at 0.1. So 998 kilograms per cubic meter times the area, pi over 4, d squared, times the velocity, and we calculate out the velocity at 1 to be 158 meters per second. And if you take a look at it, we've got kilograms. We're going to be left with kilograms per second as everything cancels out. So we're looking at 15.25 kilograms per second. We can go and calculate that out at 0.2. It doesn't matter which one we do. We're going to get 15.25 kilograms per second. So that gives us this. So now all we're left with is what is the velocity, the x component of the velocity at 1 and the x component of the velocity at 2. So if I roll back here to the picture that we were dealing with, a little too far. So if we look at this, the x velocity at 1, all of it's going to be, all the velocity at 1 is going to be in the x direction. And it's also in the positive x direction. Forgot to write my coordinate system in there, so that's all positive. Now if I look at 0.2, I have an x and y component at 0.2. I only care about the x component. I need to pay attention to the x component, though. If we look at it, it's going in the negative direction. So if we come back here and take a look at things, so that tells me that, so everything's in the x direction, so that's just going to be V1. So U2, now we are looking at that. We have to figure out what part of it's in the x direction. So we're going to use our trig. And so the part that's going to be in the x direction is going to be V2 times that cosine of the angle. And that theta is 40 degrees. But it's acting in the negative direction. So we have to, it's critically important to have those signs correct. So now let's take the equation and just rearrange it because I want my force of bolts to be positive. So I'm going to move that to the other side. So the force of the bolts is going to be equal to, I need to move that other equation over, so minus m dot times negative V2 cosine theta at 40 degrees minus V1. And then I move the pressure over, so I'm going to get minus P1A1. Now at this point, I just plug everything in. Oh, and as I was looking at the signs here, I made a mistake because we have that negative in there. I had to multiply that through. So that's going to be plus P times that. Now let's just plug all the numbers in. So the force on the bolts is going to be negative 15.25 kilograms per second. And we're going to multiply that by negative 21.7 meters per second cosine 40 degrees minus 1.95 meters per second. Look at that, units. Those are going to multiply out, and those are going to be in newtons. So that means I'll be able to add to that my pressure, which was the 233,000 e to 3 newtons per meter squared, times the area, and it's the area at 1, so pi over 4, 0.1 meters squared. And as I put all that together, I'll find that the force of the bolts is going to be 2,100 newtons. So it comes out to be a positive number. What does that tell me? Because we're dealing with vectors, that told me that I picked the correct direction when I drew it on my control volume. If this would have come out negative, all it would have meant is that I picked the incorrect direction for my vector.